So thank you, EUREKA, for the introduction. My name is Margolis, and I'm working with John Soon, my professor, and Phil Lubin in the Department of Physics and specific experimental cosmology. And we're working on measuring the cosmic microwave background radiation, or the CMBR. So the CMBR is primordial light from pretty much the beginning of the universe. And it's a little bit hard to say, but when after the Big Bang happened, the universe was expanding, but the particles were still very hot, and the protons and electrons didn't quite form stable hydrogen, and light kept breaking the bonds that did form. Eventually, the universe expanded enough so that it cooled down, where the light stopped breaking those bonds and the cloudy mixture of particles became more like something like we know now. So this light, from about 300,000 years after the Big Bang, which was about 14 billion years ago, has been expanding as the universe is expanding, and as such it's been cooling off and also being redshifted. So this particle, it's gone from, I guess, thought it was several thousand Kelvin to now about 2.7 Kelvin. And the good thing about this is that we can look up and we actually can see it. If you take up a thermometer or something that looks in the infrared region, you look in the sky, you'll see it everywhere. And it's actually, what's crazy is that it's all the same. And it's all the same within about 200 microkelvins, and this is pretty good filtering, but the thing is we don't know much about it. And this is our biggest proof to the Big Bang theory, which is still a theory. So what we're doing is actually going to be doing something else. There's not taking a temperature map, but looking at the polarization. So this is a Balloon-Borne Telescope, and what we're going to be doing is looking at some of the directions of the light. So what we have is we send the upper atmosphere, so the water isn't an issue, and the radiation comes in and bounces off our first mirror and goes into our wire grid polarizer. And what that does is it's got some plastic and then it's got some copper wire in the back, and it's spinning, and what it does is it's going to change the polarization to one polarization so we can measure when it eventually goes into the horn antenna. And so we're going to be measuring at the 10-15 gigahertz bands, which is where most of the radiation is in. And of course our sensor needs to be very good because, as it says here, it's in microkelvins. So just a brief mention of what the polarization is. And the polarization is actually the direction of the oscillation of the electric field of light, because the light has both an electric and magnetic field. And so what we're doing is basically using a grid similar to that. And the light comes in all different polarization, or what's called unpolarized, because it's in all crazy directions. And what it does is the grid gets rid of most of it, or allows only certain polarization or certain direction to go, and that's what's polarized. And what we have is it actually spinning. So we're collecting all the information and putting it into and one of the part is we have a wave plate that helps us reflect back and get all the information. We get it in the sweep, and the best part is that we can do this regardless of the orientation of where the satellite's actually pointing. So we're doing some transmission tests, and we thought about 99.9% transmission, but we were in a pre-test, we were getting about 99%. And it might not sound much, but it's actually the difference between 1% loss and 0.1% loss. And it's just that very key amount, and we're trying to find out, where it went wrong. So that's where I come in. And I'm working still on that wire grid polarizer, and I've been using computer modeling and what's called CST Microwave Studio. It's by a German company. And I'm modeling the materials and looking at the electromagnetic kind of properties and what happens. So this is a sample of kind of what it looks like. This is what the thing looks like in real life. This is just top-down view. We've got substrate and some adhesive and some wire. And this is formed when we get by companies when they take sheets. They take a sheet of the substrate and adhesive with the copper, and then they protect the parts that they want with a mask, and then they use acid in a process called etching, and they dissolve away the copper that's not wanted, and then they douse it with water. So we were thinking, our initial thoughts was that maybe there's some leftover copper or some water on it that might be affecting it. So this is where this program comes into hand, because it's so small amounts that possibly it could be, and it's really hard for us to calculate actually how it does. So we also were doing some simulation, and so in addition to the simulations, I actually tested it in what's called a vector network analyzer. And what we did is we take a little bit of the substance and we put it into a waveguide. And then what we do is hook it up in part of this, the vector network analyzer, which sends signal from this port 1. And what it does is it measures how much goes through to port 2 as for transmission, and how much goes back to that port 1 as reflection. And it goes from both sides. And what we were seeing, and so our model predicted, so I also modeled what happened. So our model predicted if it was just substrate, and he said there would be very little reflection and lots of transmission. So that's about 99.9%. And then, if there was even a little bit of copper, we'd have a huge amount of reflection and very little transmission. And if there was some water, then we would have some reflection and some transmission. But our actual model said that, well, when we actually did the test, we actually got very little reflection. We got significantly much less transmission. However, it did show that there actually was no metal or water in this kind of thing. And the transmission being off might have been actually from the calibration of the vector network analyzer. We also did some extra tests we got back, and that actually confirmed with the electron, photoelectron, X-ray photoelectron spectroscopy test that told us that there's actually no metal. So then, our next thought was, well, if there's no metal in the water, what happened if the etching actually worked too well? Because we have this acid, and it might just cut into the wire, and possibly also affect how we're getting some transmission since there's less wire. And what we found out is actually it makes very little difference. As you can see here, it's about 99.9% throughout the transmission and in 2 different modes, and it just really shows that it didn't make a difference. So right now we're still looking on how to configure it such that it would work. We've tried a couple other different things with moving the wave plate back, spreading out the wire. We haven't had any success yet, but we're hoping as it's going up in this next week and everything, that we'll get some data that can help us. We actually have my professor is actually right now in New Mexico, and he's overseeing some of the flight data that's going to be happening. So we have some. So in addition to doing that, I'm also working on some small projects that relate to it, that have to deal with some of the other components of the satellite. So this is actually an Orthomode Transducer. It helps us split the polarization as an alternative to a step guide, and this is a filter that helps us reduce the unwanted frequency. So I'd like to thank my mentor John soon, and of course all my sponsors, and EUREKA Lubin for letting me into this program, and Phil Lubin for letting me into his lab, and all the other people in my lab that helped me out. Thank you very much. Any questions? Yes.
I'm just curious, you mentioned cosmic radiation at the beginning, and it says that it's uniform in all directions. So how do we know for sure that it's uniform in all directions? What if we, from our reference point, looks uniform, but from another reference point?
We've actually tested it, and we've actually looked throughout the different parts. And the funny part is that you can look at any different. We actually look at the background, and kind of you can tell that it's the same. And it's actually the biggest. That's actually the biggest theory of why the Big Bang is correct, because it's uniform and it expanded almost like a balloon. So we've actually had satellites and everything measuring it. And you can actually see the CMDR on TV. It's actually about 1% of the noise, the static that you actually get.
The static from the TV is related to the...
Exactly. This light is actually noise. It's really cool because you can actually see it. It's there. And there's been a lot of recent satellites, but we haven't quite gotten information back yet. This is actually from a YMAP satellite, which was a couple of years ago. But right now, we're actually still processing data from the Planck satellite. that net. Send.
You mentioned right at the very end that some new data was being collected, and you were hopeful that that would help you out. Can you describe, like qualitatively, what that data is and how you're hoping that's going to help you?
Well, it's actually going to be flight data, so we're actually going to have it measuring, instead of these theoretical calculations, we're actually going to see if it measures something. This is just like kind of a beta flight or kind of a test flight. And we're hoping that, maybe we'll find some problem on, maybe our sensors are actually picking up all that we have, and maybe this is just what we thought might have been a problem, or maybe we're missing some huge factor that we haven't thought of yet. And we're hoping that any sort of data can, illuminate us on what the cause is.
Okay.
Do you know how long the test flight lasts for?
The test flight's going to be a couple hours. It's a huge balloon, but usually these flights don't last for too long. I mean, the balloon picks up at least a couple football stadiums, I'd say. It's pretty big.
So you do expect the waveguide to function well enough
Yes.
to give you data?
Yes.
And
As I said before, we're getting about 99%, and it's just our theoretical calculations said we should have been getting that extra 0.9%. So we should at least get some data, as our plastic data. What we have is actually clear and does let, in further tests, in smaller, informal tests, we have seen that it does transmit at those frequencies.
do you know in previous sort of payloads, have they used the same kind of waveguide or something similar that also hasn't, has had the same issues, and do you know how well it worked then?
I believe this is actually the first time we're actually using this kind of thing.
Okay.
This project has kind of been in the works for a long time, so we haven't exactly been able to do it. One of the problems with the VNA might have been that we were actually using a waveguide at the 30 gigahertz as opposed to the 10 gigahertz, and that is because we didn't actually have the 10 gigahertz waveguide on hand. So, further tests could help us with the VNA, the possibility. Maybe it's just at 30 gigahertz that's at 99, but maybe at 10 it's 99.9 as we expected it to be.
So with the waveguide, you show it bouncing from the big mirror to the waveguide, and then bouncing off the waveguide back to a smaller mirror. Does it pass through the wires and then bounce and then pass back through the wires?
Yes. What it does is actually, it's best seen here, and basically it goes through the wires. The wires, it's a grid of wires. The plastic goes through the plastic and everything first, and then we have what's the wave plate there, and that's a half wave plate, and that lets it bounce back at half wavelength away, so that it's going through and then it's going back out, so we can get a constant stream of information.
With the rotation of the wire between going through, being polarized, and then going back through, would there be enough of a rotation to? Because you lose some of that load.
Yes, there should be enough, because this is rotating pretty rapidly, and it's going to be consistently rotating. It's kind of doing sweeps.
Yeah. So I'm saying, when it goes through, it's polarized and bounce back. Have you accounted for that loss?
Yes.
Okay.
It shouldn't be an issue, because as the grid wire, it slightly alters the polarization. So we're actually picking up at two different points. We're actually picking up maybe you're picking up this vertical polarization, but we're also picking up the horizontal polarization. And it should, it might be a problem, but it shouldn't be too big of a problem. And I don't think it's a possibility, but it's doubtful that it could cause such a problem.
So, one last thing, just because I got to see this payload right before it left. If you could tell the audience again sort of the scale, because I think to really understand, your waveguide is quite small, right?
Oh, yes.
But then it's a part of this much larger system that's launched.
So actually, this is this is that there's actually 2 carriages, and it's actually it's I'd say about maybe 40 feet wide, and this is just for the carriage, 40 feet wide by maybe 20 feet across. It's pretty big, and this is all going to be supported by a balloon, and NASA's been patient and allowed and funded for such a thing. We actually have a twin project on the ground that's actually at White Mountain that's going to be doing similar results.
Do you know what altitude the balloon gets measurements from?
I'm not exactly sure, but I guesstimate around 100,000 feet, but I'm sure my mentor John would know a little more.
120,000.
It's a big balloon.
It's a couple of football fields, because I mean, as much as this is, it's not the lightest carriage exactly, so it's got to be big.
Yeah, it's close to the size of this room-ish, maybe half the size of this room. Great.
Thank you so much.